Chapter 12. In Chapter 4, we talked a lot about some cool scientists. You are responsible for knowing the names of those scientists, what their experiment was, and what information we got out of it. So, names of scientists. Curie. Rutherford, what did you say? Bohr, yeah. Millikan, Thomson. Okay, though Bohr isn't on our initial list, but we got Dalton, Thomson, Millikan, Curie, Rutherford. Dalton was our atomic theory. Okay, basic atomic theory. He had 5 tenets of his atomic theory. Of those 5 tenets, how many are still true? I think it's 1 or 2. Like, most of them found out to be not true anymore. Okay, Thomson. What's Thomson? No. Thomson was the cathode ray tube and the discovery of our subatomic particles, electrons, and then by default our protons. Millikan. Millikan was the one that officially came up with the charge on an electron. That was doing that oil drop experiment. Okay, that's the one you're less responsible for. Curie was radium, which was an important tool in Rutherford's experiment. And Rutherford's experiment was gold foil, determining the nucleus. Right? You are responsible for all of those ties all the way through. Okay? That doesn't mean you'll see 5 questions. I can ask 1 question that includes all of their names in it through which of the statements is true. Okay? So you're still responsible for knowing them, even though it may only show up as 1 or 2 questions. Your subatomic particles, I've divided Chapter 4 into kind of 2 sections. Initially, protons and neutrons. Protons, what do we need to know about protons? They are positively charged and they have mass. What is that mass at this stage? It's really original. 1. That's it. Neutrons. No charge and, careful, they have mass of 1. Okay, after that, and actually protons and neutrons exist where? In a super tiny nucleus. Right? The next part is our wave nature of light. This is continuous and discrete. So continuous meant example of continuous. What was that? Non-stop. That kind of works. A ramp is continuous. The visible light spectrum, a rainbow, is continuous. Okay. Discrete. Stairs are discrete. The atomic line spectrum is discrete. Because of the atomic line spectrum actually being discrete, that's when our other famous scientist Bohr comes in and says, hey, we have electron orbitals. Man, how did that go away? With our orbitals, we now have homes for our electrons. Where are the electrons located? Okay. What types of orbitals do we have? S, spherical. P, dumbbell. D, cloverleaf. F, who cares? Okay. Your subatomic particles are then your electrons, can exist in these homes. You're responsible for what those shapes look like. Okay. And then determining their electron configurations. Where do we place every single electron from an atom? Okay. Once we look at the configuration, we can break that down into 2 topics, valence and core. Why is core excluded from this? Because the core doesn't do anything. We're primarily concerned about the valence electrons. Questions about Chapter 4? That was the easy chapter, right? Electron configurations, cakewalk. That was supposed to be kind of sarcastic. Don't give me that look. Okay.
Laughing on the inside.
I appreciate that. Okay. Your electron configurations, how do we determine all of those? Your periodic table gives you all of that information. Okay? So you can either learn how to use the periodic table, chemistry class, periodic table, probably a good idea, or you memorize the crap out of a lot more information. Either is up to you. I don't really care. Okay? I'll tell you the better ways to use the periodic table. Do we have a question, guys?
Yeah, it's an exam Tuesday or Thursday.
What?
It's an exam Tuesday or Thursday.
The exam is Thursday. Thursday, not Tuesday.
I'm still worried.
Okay. That's fine. Exam is definitely Thursday. If I put it on Tuesday, who's going to show up to class honestly on Thursday before spring break?
Not me.
Yeah. Let's throw some anchor weight into that. Yeah. Chapter 5. What happened in Chapter 5? Chapter 5, you get Mendeleev organizing the periodic table. So took all that information in Chapter 4 and stashed it, buried it, hid it in the periodic table. You just have to be able to interpret it. Okay? The other big thing that Mendeleev was able to do with his periodic table is come up with predictions. So given some trend information, can't you predict a result?
Yeah.
Okay? Yeah. And you will be expected to. Trends. Okay, there's lots of trends on the periodic table. Your electron configurations contribute to that. Your atomic orbitals, your electronic orbitals. Chemical and physical properties. Okay, this comes back to the predictions of Mendeleev. Atomic radius. Okay, another big trend. Ionization energy is your other big trend. And then the last one we need to get out of our periodic table is our ionic charges. Okay? Within those, you are responsible for the trend, and you will be asked questions in the multiple choice pertaining to the exact trend. Okay? I do not necessarily expect you to be able to memorize exceptions to any of the trends, because that's mean. What I do expect you to be able to do is to understand why the trend exists the way it does. Okay? The big one being ionization energy. Okay? How do we determine our ionization energies?
Increases
The electron configurations. So you can fully expect to see a question that will likely be extra credit explaining a trend in ionization energy. Probably not the easy one. Okay? Questions about Chapter 5? Okay. Next part on our exam, which I don't have a summary slide on, Chapter 6. All the nomenclature does show up. Okay. Those of you that have done what I have asked, watch the video, and have actually done your lab for next week, should be square. Nomenclature should be a cakewalk for you. If you haven't finished that lab, finish it before the exam. Okay. And I don't mean, oh, the name of this, it says potassium bromide. Google, what is the structure of potassium bromide? That does not count as completing the lab. Okay? You need to look through the rule sets and figure out how to go through and name things. Okay? Just as a slight hint, I am not very creative. Okay? You couldn't guess that already. Okay? Which means I don't like coming up with new names for compounds, because one, I'm not creative, and two, I hate nomenclature. So I'm probably going to pull from things that I already have access to. Like maybe the lab. So if you know how to name all of those, it won't be the first time seeing it on the exam. Okay? The next lab that is officially supposed to be happening next week, and I'm fairly confident that none of you will do the lab because most of our faculty seem to not understand structure, is how do we put molecules together from atoms? Okay? That is called Lewis structure or Lewis theory. That is officially supposed to be happening next week along with the nomenclature lab. Okay? Again, general chemists suck at structure. Okay? It's horrible. Okay? But they suck at structure. And I'm not the greatest, so if I'm saying you suck at structure, there's a problem. Okay? So we need to be very careful when looking at Lewis structure I would highly encourage you to go through and start looking at that lab as well, even if you don't have to do that for next week's lab. I don't know if you will or not. Okay? Officially, it's responsible. You should be doing it. Okay? I would encourage you to look through that because that gets you a good idea on what you can expect coming out of Chapter 12 for the last of our 4 chapters for the exam. And that is happening now. Okay? The big part of that comes back to electronegativity. When we dealt with nomenclature, we need to subdivide our categories or our compounds into different categories. What are the 2 primary categories of naming when we look at our nomenclature? 2 big ones.
2 elements, or more than 2 elements?
That's actually a subcategory in the amount of elements. There's something a little bit more important before that.
What's your question?
What are the 2 major categories in naming? Metal and a nonmetal is ionic. The other one is covalent. How do we know we have an ionic or a covalent compound? Well, according to nomenclature, they're either nonmetals or they're metals and nonmetals. Okay? Which is a backwards way of saying I don't want to explain you electronegativity. Okay? But deciding the type of bond comes back to looking at electronegativity. So understanding something about the trends in electronegativity can allow you to predict the type of bond and the types of interactions that you can get from that molecule. Okay? And that's what we'll be spending some time on now when we move into Chapter 12 for our chemical bonding. So, what makes a bond?
2 elements. 2 or more elements.
2 elements. Okay, so on the left I have 2 elements. Is there a bond?
No,
How do you know there's not a bond?
because they're not together.
Okay, they're not together. So our definition of a bond is not just 2 elements, because I have 2 elements on the left. What changes as I go from left to right with this equation? Okay, we're now connecting them to each other. How are they connecting? Electrons. Okay, the outermost shell of the electrons are now interacting between those atoms. Okay, if we went on and drew some colored dots, so there's an electron on that one, there's an electron on that one. If I get these 2 atoms close enough to each other, what can happen? That blue electron sees the nucleus of the other one and says, hey, I'm going to go check out that positive charge. What does the purple one do? Goes the other way. It says, hey, I can check out the positive charge over there on that nucleus. Those electrons are now being shared between the atoms. I've now defined a bond. Okay? Yeah, I appreciate the excitement. Okay? That's what makes a bond, is the electron sharing. Okay? Well, in the next question, are all bonds the same? Okay? In that first case, would I expect to get the same type of bond as I get in this bottom case? Okay, you're shaking your head no. Why not?
Because those are 2 different.
I colored the balls differently. So of course they're differently. They're differently. Why not? Okay? Yes, that's exactly right. Okay? Something is changing about our elements which changes the characteristics of how the electrons are being shared between the atoms. Because that is now changed, I have to change, number 1, my nomenclature system and how I would classify that molecule. Why do I care about how it's classified? Okay. Well, do you care about the classifications of, say, water and acid? I hear somebody laughing. Why are you laughing? Is that something you care about? I gave you a beaker of acid and said, go ahead, have a drink. Be like, oh, sure, why not? Okay. We look at classifications. Why is there a classification there? Acids are dangerous. I don't want to kill myself with an acid. Okay? So we come up with these classifications to understand something about the reactivity of the molecule. That's why we classify. It's not just to make your life difficult. It's to make sure you're not dead. Okay? So, our types of bonds. Okay, we end up with 2 main categories, ionic bonds and covalent bonds. The rough bulk overlay picture for this is your ionic bonds are when you take a metal and a nonmetal. Your covalent bonds are when you take 2 nonmetals. Does this cover all of the possible bonds?
No.
What's the one I'm missing?
Hydrogen.
Ooh, interesting statement. Hydrogen bonding. Okay. Nice little fun pet peeve on that one. Guess what type of bond hydrogen bonding is? It's not. It's not a bond.
It's just hydrogen.
No, it's not a bond, period. Okay. Why do we call it hydrogen bonding? Because some crackhead idiot decided to call it something similar to a bond to confuse the hell out of everybody. Okay. It is not a bond. Okay. There is another type of bond, though, that we didn't reference. What happens if you take a metal and a metal? That's not described up here. What kind of bond do you get there? I want to be real creative with this one. It's a metallic bond. Yeah, that was awesome. Why do we not talk about metallic bonds? I beg to differ. We get a lot of different metal-metal bonds. Why do we not look at them? Do you really want to look at yet another thing in this class? I mean, we're going to be honest. Let's try and simplify a little bit. We'll save the metal-metal types of bonds and interactions for other classes, like material science. Okay? So we're picking the bulk categories because we can deal with those a lot easier than we can with the types of reactions that happens between metals and metals. Okay? So the next thing that comes out of this is you'll see two references. Molecules typically gets reserved for, at least within our textbook, for some stupid unknown reason, to covalent compounds. Ionic compounds won't get referred to as molecules. Why? When you look at an ionic compound, it repeats. When you look at a covalent compound, it doesn't repeat. The structure ends with water. If I look at salt, it doesn't end with sodium chloride. It continues out. Sodium chloride, sodium chloride, sodium chloride, all the way out. Okay? Water doesn't go HO, 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 HO. Okay? We just get H2O and it's done. Okay? It's a distinct unit for a covalent compound. We refer to those as our molecules. The ionic compounds, because they have this repeating nature to them, calling them a molecule sorta isn't accurate. Okay? So our textbook has decided to add some confusion to that by calling them formula units. What is the difference between a formula unit and a molecule? Formula units really just apply to ionic compounds. Anything beyond that? No. For all intents and purposes, they mean the same thing. Okay? You absolutely should not call water a formula unit. But it is okay to call an ionic bond a molecule. Okay? Just so you know. Just because it's up there, and I keep always forgetting to mention that. So, are all non-metal covalent bonds the same? So we got two nice examples down here. H, which is a nonmetal, O, which is a nonmetal, and we end up with covalent bond, right? Water. H, which is, yeah, fair enough. Nonmetal, and Cl, nonmetal, so we have a covalent bond, right? Two compounds, covalent bonds, are all covalent bonds the same? Why are you saying no right away with those two examples?
H2O is water.
H2O is water and
That's different.
HCl is not water, good enough, is hydrochloric acid. This goes back to the acid versus water issue. We get drastically different reactions coming out of those. Why? This goes back to, whoop, too far. Electronegativity. It's the difference in electronegativity between our atoms that gets us some classification behind what types of reactivity we get. Okay? So we'll attempt to come up with some bulk classifications. Realize we kind of have to needle our way through on some of those. So our ionic bonds. Okay? When we look at an ionic bond, we're looking at a complete transfer of electrons. Why is transfer in bold? Dang, you shattered that.
Giving or taking electrons, not sharing them.
You are not sharing electrons. One atom rips the electrons away from the other atom. But what did we say a bond was? Sharing of electrons. This puts ionic bonds in a really weird spot. Okay, because we're referring to it as a bond, but by definition it is not sharing electrons. Really odd gray area. Okay, but that is where the ionic bond sits. Your ionic bonds are composed of two pieces, a positively charged atom or atoms, and a negatively charged atom or atoms. The positively charged atom takes way too much time to say, so we refer to it as the cation, or I've heard people refer to it as a cation too. Okay? I can see it, cation. That makes sense. Okay? Well, that's fine. I'll talk to you after class about it. Okay. How can we remember that cations are positive? Okay. I still think this is dumb, but I'm going to do it anyway. Because cats have paws. Paws. Someone actually drew it, and I was like, okay, I'm going to kind of see it. Right? I keep getting people telling me that that looks like a cat eye with a positive charge, and that doesn't make any sense to me. But cats have paws. That's a Ninja Turtle, but... Okay, so cats are positive. The negatively charged species is referred to as the anion. Okay? You need to pass those up, and there's no animal to go with anion that I'm aware of. Typically, I stand corrected. Anion, animal. No, that didn't work.
Just do onion.
No, sorry, didn't work. Anions are negatively charged. Your metals almost always will carry the positive charge. Okay, what is that almost? Maybe like a fraction of 1% of the time. Okay, will they not be positively charged? Every time I can see in a standard case, they are positively charged. Okay, why might they always be positively charged? What do you mean the table?
They have less than their valence.
If we go back to our electronegativities, the electronegativities of all of your metals are lower than everything else. Their electronegativities are very, very low, meaning they do not attract bonding electrons, which means whatever they're bound to takes the electrons away. They carry the positive charge. Okay? So due to the regularity of these charges, that's where we end up with these extended crystal structures. So if I wanted to just provide the formula for the compound there, okay, and we labeled this out as sodium chloride, okay, just to provide the symbol for this. Okay, let's just do the symbol for the face of this thing. What would our symbol be? Na 5, Cl4. Oh man, that's a lot of numbers. Okay, that didn't even take into consideration all of the layers behind it. Okay, which is why we say it's nonsense to specify all of the atoms in ionic compounds, because they have too much of a repeating lattice. So what do we report? The reduced ratio between them. And when we look at sodium chloride, the extended lattice will always come out to a ratio of 1 sodium to 1 chloride. Why is it only 1 sodium to 1 chloride? The charge on chloride is -1. The charge on sodium, +1. Why is it 1 to 1 of each? Because 1 of each gives me a neutral charge. Okay? Ionic radii. So let's look at our sodium chloride again. Okay. If we look here, sodium is the big one, chloride is the small one. If we go back on that previous slide, didn't I have it labeled the other way around? Yeah, I did. Oh, that was kind of weird. Why did I do that? What happens when I go to make sodium chloride, when I react sodium atom with chloride atom? It's an ionic bond. What happens to the sodium? It becomes a cation. How does it become positively charged? Hey, if you get to remember it.
It has less electronegativity than chlorine.
Sodium is lower in electronegativity than chlorine, so much lower that when I bring the sodium atom near the chlorine, what happens? It loses its electron. Which electron did it lose? It's outermost. It's valence. Good answers. I want more specificity. Look at its electron configuration. Which electron did it lose? The 3s electron. So the electron configuration becomes isoelectronic to neon. What happens to the radius as I go from sodium to neon? Left to right, it decreases. I'm going left to right, so it should get smaller. Okay. I'm also going up, which means it decreases even further. So the radius for the sodium cation is significantly smaller than where it started. What happens to the anion? Well, we had our chlorine atom with our configuration of neon. Oh man, this is a lot longer. And that's supposed to be a 3. 3s2, 3p5. And it becomes neon. Our chlorine being more electronegative than the sodium does what? It takes the electron away from the sodium. Where does that one extra electron go? Into the p orbital, and I end up with my electron configuration being 3s2, 3p6. Okay. So it would now look like argon. What would we predict happened to the size as I go from chlorine to argon? Chlorine to argon, what happens to the size? Ignore what's up on the screen. Chlorine to argon, atomic radius. It decreases. What happens to the radius here? It increases. What the heck happened? It took the electron, so it looks like argon now. Chlorine versus an argon atom, argon is smaller. Why does the radius get bigger when we go to the anion? Am I looking at chlorine and argon? I'm looking at chloride and argon. When we went from a chlorine atom to argon, what changed? We added an extra electron where? Into the valence shell, the same energy level. But when we go from chlorine to argon, what happens to the nucleus? It gains a proton, so the atom or the electron gets sucked a little bit tighter. When we look at the chloride ion, we add an extra electron. Do we change the nucleus? So now the nucleus, no longer as positive, can't hold that negative charge as tightly, and what happens? It drifts a little bit further away. Our radius increases. Okay? So this comes back to understanding why we have the trends we do by looking at the electron configurations and realizing it's not just where the electrons are located, but it's also their relationship back to the nucleus. Okay? You have to keep that in consideration. Okay? The other thing you do is just memorize the trend. As you go from a neutral structure to a cation, what happens to the radius? It decreases. As you go from a neutral structure to an anion, what happens? It gets bigger. Ta-da! Done. Okay? Questions? That looked kind of like a mind-blowing step. How are we with that? Are we good enough? We want to move on? You just want to accept that? Let it go. Okay. What we're trying to do is predict what happens. So where did I lose you? Are you okay sodium going smaller when it becomes sodium ion? Okay. So it's the chlorine atom that's weird. Okay. So chlorine going from chlorine atom to chloride ion. Okay. The chloride ion is isoelectronic with argon. So it looks the same as argon. So if we try and pull back to our understanding, Why does chloride get an extra electron? Okay, there's two answers to this. Number one, it took it from sodium. Okay. Number two, we're saying it's chloride. Why does chloride have an extra electron? What's its charge? -1. How did it become negative? By gaining an electron. So we have two kind of answers to that. We can just say, let's look at chloride on its own. Chloride on its own is -1. It had to have gained an electron. Where did it come from? We'd have to look at a reaction. That's when we could say, in this case, it's coming from sodium. Okay? So you okay with that part?
I just wondered, did you say that from a neutral metal to, or like for sodium, to become a cation, the radius decreases?
To go from
Is that what you said?
a neutral species to a positive species, neutral to positive, what happens? It will get smaller.
Okay, and then vice versa for
Neutral to negative,
will get bigger.
it gets bigger. That will always be true.
Okay, I just want to make sure I heard that right.
Nope, you got it. Okay, so if we go back to why chloride got bigger, our electron configuration for the chlorine atom, okay, whatever defined it was. When we became the chloride ion, what's our electron configuration? It becomes argon. So the gut would be to compare, like we did with all of our atomic radii, and compare now the radius of a chlorine atom to an argon atom. Okay? And we do that comparison from our trends. What is the relationship between a chlorine atom and an argon atom? Argon is smaller. So we might have said that when we become a chloride ion, it should get smaller. But are we becoming argon? No, we are only becoming argon's electron configuration. So when we move from a chlorine atom to chloride to look like argon, all we've done is increase the number of electrons. Have we changed the nuclear charge? No. The nuclear charge is what's pulling the electrons tighter. So when I go from chlorine atom to argon, the argon nuclear charge is pulling the electron tighter. When I go from chlorine atom to chloride, I may be adding that extra electron to look like argon, but I don't have the nuclear charge to hold it. Okay? If I don't have the charge to hold that in tighter, where does the electron go? Further away. So the radius ends up increasing when we look at our radii on going from a neutral species to an anion. Okay. We don't have enough nuclear charge to hold those electrons. Okay. That's it. Right. You feel a little more confident? Okay. Okay. You already had to talk to me after class about something else we talked about, so we can do that. Yeah, we got to do it on this now too. I at least got 5 head shakes yes, so I'm good with that. Okay. Covalent bonds. Ready? I have no idea how to compare this. So I said the ionic bonds were your 5-year-olds not really sharing anything. Covalent bonds, I mean, if you get younger, right, kids share what they share. I mean, certainly older doesn't share. Okay. But our covalent bonds are now sharing electrons between atoms. Okay. Well, if we share electrons, do the atoms gain or lose electrons? No, because it gives one up, but then it gets one back. Okay. So what happens to the radius?
Doesn't change.
Doesn't change. It'll stay the same. Okay. So we aren't looking at a radius anymore when we're trying to determine the relationship between our nuclei. But what we can look at now is something known as the bond length, the distance between the nuclei in the new compound. Okay. What might we predict to happen for the distance between the nuclei? Well, if we had 2 atoms near each other, without forming a bond, they're going to be really far away from each other. Let's bring them real close to each other, and now let's put them just so the outermost edge touches each other. The distance between the nuclei would be what? I take two spheres and I bring them near each other. When those outer edges intersect, what's the center to center distance defined as? The radius of one plus the radius of the other. Basic geometry. Okay? So if we were sharing electrons, we might say, okay, well that could be our bond length. So what we went through and did was tested it. We took a compound, HCl, covalent bond, and we let it form a bond, and then we looked and measured the internuclear distance, our bond length. If we just add up the radii of those two atoms, what do we get? 0.136 nanometers. Okay? Tiny distance, 0.136 nanometers, it's pretty small. Okay? That would be the sum of our radii. When we look at the actual bond length, what is it? You could tell me the number, because it's up there. The other option is, is it R1 plus R2? No. How did it change? It's smaller. Why should the bond length be smaller? I'm taking the electrons of one atom, and those electrons, while still connected to our nucleus, are being attracted to the nucleus of the other atom. Which means as they shift to share with the other atom, it's also dragging the nucleus with it. Which then means what happens to the distance between the nuclei? It becomes smaller than the sum of the radii. Okay? If we had a very weak attraction, say like an ionic bond, we could look at the bond length in between, and it would just be the sum of the radii. In a covalent bond, it's a stronger interaction because we're sharing electrons. That stronger interaction is necessarily going to bring those two nuclei closer. And that's it. That's all we're trying to get out of bond length.
So ionic, one takes an electron, and covalent, they share.
Exactly right. Ionic, transfer of electrons, or taking electrons. Transfer is an important word. You may want to remember that for like 8 weeks from now. Okay. And covalent is a sharing of electrons. Okay. Other questions? Okay. This is a fun one. Bond energy. Okay, what do we think would happen when we do a reaction here? So we've talked about energy before. What do you think would happen to the energy when we do this chemical reaction? Should we require energy? Should we have to add energy to this, or should it release energy? Why should it release energy? What if it didn't release energy? Okay. By releasing energy, we're saying that our product is lower in energy than our reactants. Why does that make sense? Why should our product be lower in energy than our reactants?
Because you need the energy to get it.
No, that's actually the converse. By putting them together, we release that energy. It leaves our reaction. It wants to be neutral. And our neutral species are lower in energy. So by making a bond, we should transition to a lower energy state. We don't want to go to a higher energy state. Okay? If you were walking around outside and some random invisible hand came up and grabbed you and held you 100 feet up in the air, you'd probably be unhappy with your life fairly frequently and wondering, why is this hand grabbing me and when is it going to stop doing this? Okay? That's not a happy state. You are happy on the ground with control of your own destiny. The same thing's happening here. Okay? We want that lowest energy state. Okay? Why does it make sense that we're now moving to a lower energy state? How many atoms are in your body? A lot. Are those atoms just atoms on their own, or are they in bonds? They're in bonds. What do you think? If we exist as bonded structures, Should bonded structures release energy? Yeah. Okay. If they didn't release energy, our atoms would not want to form connections. If our atoms don't form connections, do we exist? No. We have direct evidence that our atoms, in the process of making a bond, will release energy. How can I write that into my equation now so that I can see that energy was released? How under the arrow? That's actually new to me, so I need more description. Okay, we could say release energy. A, right?
Yeah.
Release energy. Okay, there's another way we can do it. Put energy on the product side. When the reaction occurs, what forms? Energy. There it is. Energy is released. Okay. What if I had written energy on the reactant side? Energy had to be absorbed to allow the reaction to occur. Now let's go through and remove the equation altogether, and I want to say the change in energy for this reaction is what? Okay, and I'll be a little bit more helpful. Let's actually make a number there. Let's say the energy is 100 kilojoules. The change in energy for this reaction is now what? It is negative 100 kilojoules. Why? Energy was released. What does that negative mean? The energy term is a product. That's what the negative means. That's it. Just telling us where to put the energy term. Okay? Some mathematician will come through and tell you some other weird nonsense about the negative sign. All it means is that it was a product. What if the energy was a positive? It was a reactant. That's it. That's all the sign means. Where does the energy term show up in your equation? Okay, that's it. So when we look at our bonds, we can look at the formation of a covalent bond from the individual atoms. They will always release heat. Okay, that is an exothermic reaction. Okay, if I wanted to break that bond, what's going to happen? Well, what would my equation be if I'm going to break the bond? What do I start with? HCl. What do I want to end with? Hydrogen plus chlorine. Where was energy in my equation? My heat. It was a product originally. Now it's a reactant. All I've done is switch the equation around. So if I reverse my reaction, what happens? It's now just going to change where the energy is. To break a bond, I need to add energy into this. That's all we're looking at. Where's the relationship of heat with respect to our reactants and products? Okay. This is known as our bond energy, and that's pretty much it. Okay. I can reference that top equation by a particular name, referring to the thermicity, or the heat exchange. What happened with the heat exchange? The heat was released, so the heat left, went to the outside, also known as exothermic. In the other case, heat was added into the reaction, put to the inside. It was known as endothermic. Where does the heat transfer? Okay. If we're looking at just an energy term, okay, or a change in energy, but we aren't given a context of the reaction, we may see our endothermic reactions referred to as a positive energy change, and our exothermic referred to as a negative energy change. Remember that negative sign? Yeah, it sneaks back and bites you again. Okay. Questions? Okay, let's get out some of this boring stuff. All bonds the same? No. Okay. We have three primary classes of bonds. Okay. We have ionic, and we have covalent. Now you only said two things. I said three things. Do our covalent bonds subcategorize? Yep. How do they subcategorize? Based on polarity is determined from this based on electronegativity. Okay. How do we know we have an ionic bond? Quick, go. Define ionic.
Metal, non-metal.
Metal and a nonmetal. Wow, that worked really well. I'm going to say quick, go a lot more often.
Oh.
Metal and a nonmetal. Is that always true? No. Okay. But take your metals and nonmetals and look up their electronegativities and look at the difference between them. You will find that for most metal-nonmetal bonds, the difference in electronegativity is greater than 1.7. The strict definition on what makes an ionic bond, the difference in electronegativity is greater than 1.7. Okay. How many of you want to memorize electronegativities? Actually, I'm going to put my hand down. Nobody? Really? Nobody wants to memorize? You want to memorize? Okay, you can memorize them. Nobody else memorize the electronegativities. It's a waste of time. Okay. What we want to do is come up with a quick rule of thumb so we don't have to memorize some more useless information. Okay? An ionic bond is metal and nonmetal. The other classification we had was covalent bonds. Okay? Well, how do we know we had a covalent bond? Nonmetal, nonmetal. Okay? So we could write under polar covalent, because it says covalent, nonmetal, nonmetal. What would we write under nonpolar covalent? Nonmetal, nonmetal. Are those different? No, so that sucks to write. Don't write that. Okay? We want to come up with something better that allows us to distinguish between those two. Okay? A nonpolar covalent means that they are equally sharing electrons, but not all nonmetals will equally share electrons with each other. There's something going on with that. That something comes down to their difference in electronegativity. So our nonpolar covalents can be written down as less than a difference of 0.5. Okay? Bridget, you got to memorize already. Which ones are less than 0.5? Did you actually attempt to memorize them already? I was just kidding. No, I didn't expect you to memorize. Wow. I was like, okay, good, good.
I was wondering why you're asking me. No, I didn't.
Okay. That's a really hard definition to try and remember. They are equally sharing electrons. What happens if I put a carbon near a carbon? What's their difference in electronegativity? 0. Is that less than 0.5? Yeah. How about fluorine? Fluorine, the most electronegative element on the table. I bond it to fluorine. What's the difference in electronegativity? Fluorine and fluorine, the difference is 0. Any element bound to the same type of element will get us a 0 difference in electronegativity, which means that type of bond is nonpolar covalent. Less than 0.5. And that's because when we try to put molecules together, we do very often put the same atom next to the same atom. Okay? But there are other cases that don't get enough polarity to them that they pick up some reactivity. That one extra case that we want to remember for our nonpolar covalent, so same to same, and this is where our 0.5 comes into play. So we need something else. That something else is going to be carbon to, did you get the electronegativities memorized yet? Hydrogen. So if I find two atoms, same type of atoms, and I bond them to each other, they are nonpolar covalent. If I take a carbon and bond it to a hydrogen, nonpolar covalent. Okay. What type of bond do I have between magnesium and sulfur? Not to give any hints. Ionic. How do you know it's ionic? Magnesium's a metal, sulfur's a nonmetal. That's an ionic bond. Yes?
Can you repeat, what decimals mean though? Greater than?
Those values are your greater than, less than differences in electronegativity. Okay. Oxygen to oxygen. Nonpolar covalent. Carbon to hydrogen. Hydrogen to carbon. I'm just checking. Hydrogen to oxygen.
Polar.
How do you say that was polar covalent?
I don't know, I guess.
Is it ionic? No. Is it nonpolar covalent? No. So that means it must be polar covalent. What's our definition for polar covalent? Yes. Everything else. If it is not ionic and it is not nonpolar covalent, it is polar covalent. That is your definition. Does that kind of suck as one? Yeah. But does it cover nearly everything you would possibly need to do and use? Absolutely. It is phenomenally accurate in that respect. Okay? Everything else. We will use those definitions to help us classify how compounds react with each other. Okay? How could we potentially do that? Well, if we look at a magnesium-sulfur bond, it is an ionic bond, meaning the magnesium must become a cation. Cations are positive. I love the head shake too. Sulfur then becomes negative, an anion. If we take a look at the HO bond, that one's a little bit tricky. Let's skip the HO bond for a moment. Let's take a look at the CH bond. What happens to the CH bond? They're sharing electrons equally, right? Does any one of those atoms become charged? Nope. What would I expect when I mix, say, an ionic compound into a solution versus a nonpolar covalent compound into a solution? Which would have a stronger interaction or a stronger desire to react? The ionic, because it's charged. Just looking at the type of bond gets us an idea of the reactivity. And in the nonpolar covalent, there is no charge because they equally share electrons. What happens when we move to the polar covalent? It is still covalent. What is that polar throwing in there?
They don't share equally.
They don't share equally. Well, how are those electrons then shared if not equally? Unequally sort of fair. Which direction are they shared?
To the bigger.
Bigger is dangerous. Don't say bigger. To the more electronegative atom. Which element is more electronegative, oxygen or hydrogen? Oxygen. So oxygen is taking most of the electrons most of the time, which means the oxygen starts to become, by taking the electrons, it becomes negative because electrons are negatively charged. So I could add information to this by saying a negative there, and what would the hydrogen then become? Positive. But if I use that notation, that starts to look, like an ionic bond. Is it an ionic bond? No, so I can't use positive and negative. So what I'm going to use, it's only some of the time kind of negative, and some of the time kind of positive. So the symbol I choose to use for that, some of the time kind of negative. There we go. There we go. Well, I'll just write SOTCO next to every single one of my signs. Or it is not an 8. I heard it. It's a delta. It's a lowercase delta. What did we say delta was? Change. What's happening here? It's the change in the dispersion of the bonding electrons. One way it's changing to gain electrons, it's becoming negatively charged. The other way it's becoming positively charged. This is our delta notation. All we're trying to do is say where are the charges aligning. Why is that important? If I throw this bond into a compound or into a solution, what's going to happen? A reaction where the negative is going to seek out a positive. I can predict reactions with this. Boom. Amazing. That was kind of an incredulous laugh. I'm not sure I quite accept that. Right? So, now what we've got to do, that we got a basic idea of bonding, is how do we put these together into molecules? So this is where Lewis got a little bit crazy on us. Lewis went through and said, okay, we've got atomic structure. We got protons, we got neutrons, we got electrons. That's an atom. How do I get these two atoms to now interact with each other to form bonds? Right? Well, he started with the simplest assumption. If I take two atoms and bring them near each other, what interacts between those atoms first? The electrons, and in particular, the valence electrons, the outermost. So he spent his time only looking at the valence electrons. Take the next step to this. Look at these examples that we're referencing here. Where are all of those examples located? Sort of the right. First two rows. We didn't go any lower than the first two rows. Why? What happens when you go into the third row? Dun, 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 dun. D orbitals. Dun, dun. The d orbitals throw a whole big monkey wrench into this and make it more confusing to look at. So he kept his focus in those first two rows and tried to predict a bonding theory using just those two rows. Right? And when he went through and looked at it, he said, neon. Neon's an interesting fella because neon stops reacting. Everything else, whoosh, tons of reaction. Neon doesn't react. Well, neon had how many electrons?
10.
In its valence shell. So now we're running into some interesting. How do we determine the valence shell? The valence shell is looking at our highest energy level electrons. What energy level is neon in? The second energy level. How many electrons are in the second energy level? 8. How do you know there's 8? Oops. So you could subtract 2 from the total. Take a look at the column that neon's in. Very top of that, right above helium. What does it say the number is? 18. Okay. 18, right? The very, 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 very top, above helium. Okay, what does it show next to it in Roman numerals? 8. If you know how to read Roman numerals, it says 8. We just said neon had 8 valence electrons. How many electrons for fluorine? 7. What's the column number for fluorine? 17. Roman numerals? 7. Ooh, 7. How many valence electrons for boron? 3. Column number? 13. Roman numeral? 3. The column at the top is going to tell you how many valence electrons you have. Kind of nice. Our orbitals hold how many electrons? 2. So we're looking for something that has 4 potential interactions. Okay? Because we've got 8 electrons. Okay? He went through and said, well, I can take those 8 electrons and I'm going to put them on a shape. The shape that he picked was a cube. Why would he have picked a cube? Yes, I think there are 8 sides. There are 8 points on a cube. So he went through and said, okay, for hydrogen, its electron shell is 1s1, right? So I'm going to draw on hydrogen's electron. There's hydrogen's electron. Fluorine has 7 electrons. So I'm going to draw on the 7 electrons for fluorine. What happens is I bring these 2 cubes near each other on that one vertice. In one case, there's an open hole on the fluorine. The red hydrogen electron can come in. In the other case, there's an open vertice on the hydrogen cube, and that can pick up the blue electron from fluorine. What have we now formed? A bond between hydrogen and fluorine. Cool. Now do CH4. CH4, you're now going to take 5 of these stupid cubes and try and put them all together. And you say, well, okay, this nice theory. I agree with it. I appreciate it. But let's simplify that down. Let's get this down into 2 dimensions. What 2-dimensional object has 4 sides?
Well, a circle doesn't, but
A square. A square. The flat version of a cube. And what do we end up with? The new notation for Lewis structures. Fluorine, hydrogen. I put my electrons around. There's an empty hole. There's an empty hole. I now have a pair of electrons between the atoms, and I now have a bond between those atoms. All based off of a cube, which we then compress down to a square. The square is a very important shape when dealing with Lewis structures, particularly in this class. If you move up to 151, they turn it into a whole nother crap storm. Okay? But at this point, we can keep it relatively simple. We now have the basics of how to draw Lewis structures. Now all we need are the rules. Here are the rules. Okay? And everyone goes, oh my God, that looks ridiculous. The textbook's rules are so much shorter. Yeah, they're also wrong. Okay? Well, the tutors gave me better rules. The tutors gave you rules based on how they know the answer to be. When you take the test, do you know the answer? No. Which means you're SOL. Follow these rules to the letter. There are very few cases where the letter following of these rules takes you to the wrong path. The biggest reason behind these rules on why you should follow them comes down in number 6 and this concept of resonance that is stupidly difficult that will show up on 2 exams, both exam 2 and exam 3, because it is really important. Anybody dealing with organic chemistry needs to understand resonance. You are now at the fundamentals to start that path. Okay? If you do not follow these rules and you have to move into organic chemistry, I promise you, you will screw up. These rules work all the way through. Okay? Why does nobody use these rules? Because most general chemists don't understand organic chemistry. Okay? So they ignore this topic because they're like, well, there's an exception. There's not an exception. Follow the rules. It works. Okay? So we got 10 minutes. Let's see what we can go through and do. Next big thing. Talking to tutors. You should still talk to tutors. Make sure you've got this little direction sheet in front of you so that they can help walk you through it. But here comes the next big wrinkle on this. Are these rules consistent from class to class to class? No. Okay. I am the only class that puts these rules out. Okay. I think there's one other faculty member that uses my slides, so she might use them, but I don't think she knows how to use them. Okay. But she at least has them. Okay. The other sections, don't go through them all the way. Okay. Well, let's say 151, still the same idea. You're still getting to a structure. The issue comes down in this last step, how much you are responsible for. Okay? You are not responsible for assigning formal charge to atoms. Because you are not responsible for that step, there's a lot of extra steps that you don't know how to do. So when you talk to a tutor, either in our tutoring center here or to tutors that you're paying outside of class, you need to tell them they need to follow these rules and they need to be very careful with what they're showing you. Because there are certain molecules that if you look them up on Google, you can't get that answer based on the rule sets you've got. And that's because you don't know how to distinguish between Lewis structures. You don't know that yet. Would you learn that in 151? Probably not, because the 151 instructors don't want to spend time talking about it. Would you learn about it in organic? Yeah, and I flip my crap every single time trying to go through and make sure you get it down right. Okay? Follow the rules. Be very careful that you are not responsible for assigning formal charge to atoms. So, let's take a look at these. We got our little cheat sheet. We now are going to jump to our first molecule, CF4. What's our first rule? valence electrons. So I need to figure out the valence electrons for every single atom. Well, how many valence electrons does carbon have? 4. How'd you get 4?
Because I looked at the periodic table.
I will agree with looking at the periodic table. Give me a little bit more.
The Roman number.
That's the number above it. Yeah, column 14. Cool. I agree. 4. Fluorine. 7. How many fluorines are there? 4. So should I just be adding 7? No, I have to count for the valence electrons for every single atom. So I could do 7 plus 7 plus 7 plus 7, or times 4. Which, 28 plus 4, 32. Okay, at this point, I do not care about valence electrons anymore. All I care about is this magic number of 32. That needs to get fixed. Step 2. Central atom. I need to pick a central atom. Almost everything that you will be dealing with will have a central atom. When it comes to the exam, you will have a central atom. Okay? So no strings of atoms. You have one central atom and you have put a bunch of stuff on the outside of it. Okay? Our central atom needs to be the least electronegative. Which atom is least electronegative, carbon or fluorine? Carbon. Right? Because fluorine is the most, so it clearly can't be that one. So carbon needs to be my center atom. Now what I want to do is add or scatter my fluorine atoms around my center atom. Does it matter where I scatter them? Not really. But for the sake of organization and neatness, I'm going to scatter them in this particular fashion. Why? I heard someone say it. I'm putting the atoms on the face of a square. That's it. Okay, why? Lewis structure is based off of cubes and squares. That's why. Okay, it also solves like half a dozen other problems later on down the road. Okay, so I'm placing my atoms on the face of a square. Okay, now I want to add electrons to my structure. Okay, and this is where I differ so much from other textbooks and other references. I want to add the electrons where? The most electronegative. Electronegativity had to do with, defined as, holding bonding electrons. So if I'm trying to put electrons into a structure, where should I put them? Probably on the atom that wants the electrons. That's going to be the most electronegative. So I'm going to start adding my electrons in pairs to the most electronegative. Which fluorine is the most electronegative? Trick question. They're all the same, so it doesn't matter. Start drawing them in. And I will add them up until this point on that particular fluorine. Why do I stop there? Okay, remember, Lewis kept the first 2 rows. And in the first 2 rows, how many electrons can we get for the second row? 8. How many electrons are around that fluorine right now? 8. It's called the octet rule. We must achieve the octet rule. I now move to the next fluorine atom. 2, 4, 6, 8. Satisfy the octet. Move to the next atom. Move to the next atom. How many electrons do I have? 32. Have I put in all the electrons I need? Yep. So now what do? Anywhere there's a pair of electrons between atoms, I will convert into a line to represent a bond. So line, 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 line. Now what I will do is check octets. Okay? How many electrons around the fluorine? 8. The other fluorine. Other fluorine. Other fluorine. Carbon. I was waiting for that pause. Why did you not say 8 right away? That's fine. Don't want to be wrong? Okay. The electrons in those bonds are shared technically at this point equally between the atoms, which means I will count those electrons to both atoms. Okay? So when I count carbon, I've got 8 electrons because there are 4 bonds, and each of those lines represents 2 electrons. So there's 8 electrons around that carbon. Around the fluorine, I have 1, 2, 3, 4, 5, 6 electrons that are not in bonds, and 2 that are in bonds. So I have 8 electrons. Does every atom have its octet? Yep. I'm now done. Ta-da!
So that's why you put 8 around all of them, so that way the carbon gets 8 electrons?
So the carbon will end up having to get 8 electrons. Yes. And I kind of want to sneak into, I think, maybe that guy.
Why did you, if we're just counting the total valence electrons, carbon has 4 and fluorine has 7.
Mm-hmm.
Why was it 32? Maybe
How many fluorines were there?
Oh, okay. Got it.
Hi. Questions? Yes.
So then it's not necessary to place the 2 electrons there, just the lines to connect the 2 of them?
Between. Sorry. You're welcome. It is not necessary to place the 2 electrons in there. You'll notice that I go through to do it with an eraser and all of that to help with the pattern behind it. I don't want you immediately drawing lines because that's when you start to make mistakes. The other common thing that you'll see very old school chemists do is anywhere there's a pair of electrons, they'll turn into a line. Meaning the final structure that they draw looks like this.
That would be incorrect, right? Because no bond there.
It comes down to what we define as a line.
Okay.
The old school chemists say the line is a pair of electrons. That makes things confusing. New school chemists, or smart chemists, I just ripped on a lot of people that work here. That was bad. Feel free to pass it along. Want to be able to see the difference between non-bonding electrons and bonding electrons. So that's why I do not show them as lines. Most of the faculty here, I think, oh, that was the wrong button. I think all of the faculty here will show them as dots, not as lines when they're non-bonding pairs.
Okay, so then you do not want the dots, only the line? Is that what you want?
When it is a bond,
Okay.
you need to show the line, not the dots. Only when it is bond. If it is not a bond, you can't show a line. You need to show the dots. Okay, we are almost out of time, so I'm going to rip through real quickly SO3 because I think this is a good one to kind of confuse you and make you go, what? Feel free to jump in. Thank you. Sulfur has 6. Oxygen has 6. There's 3 of them, so I get 18 and 6. 24 total electrons need to go into my structure. Everybody good? Sulfur will be my center atom. Okay? It's a little bit tricky nailing that one down, but you could look at your electronegativities. Sulfur is less electronegative than your oxygen. Oxygen's the second most electronegative. So I'll put my sulfur. I'll scatter my oxygens on the outside. Okay? Again, I'm aiming for that square face. It doesn't matter which face, but I'm getting that square face. I'll put my electrons in pairs. 2, 4, 6, 8. I'm counting too fast. So I'll slow that down. There's 16. And there we are now at how many? 24, right? Did it catch up? Anywhere I have a pair of electrons between atoms, I can turn into a line to represent the bond. Before I say my structure is done, I now need to account for my octets. Does my oxygen have an octet? Does the other oxygen have its octet? Does the other oxygen have its octet? Yes. Does the sulfur? No. Here's our rub. This is where 6 comes into play and this concept of resonance. Sulfur is missing its octet. Do not, under any circumstance, go, well, hey, just add 2 more electrons. Because that changes the number that you were told to start with. You could only put in 24. By adding those extra 2, you've now made it 26. So we need to move electrons. Well, crap. So I'm going to erase a pair of electrons on the oxygen. I'm going to put it on the sulfur. Does my sulfur have its octet? Yep, so now everything's happy, right? No, because I screwed up the oxygen. I need to place that pair of electrons in such a way that both the sulfur and the oxygen share them. Put it into the space where between the atoms. Which pair of electrons should I move? From the top oxygen, the right oxygen, the bottom oxygen. It sort of doesn't matter. Does it result in a different looking drawing? Yes. Guess what you just discovered? Resonance. Which structure do you have to provide for that your correct answer? All three. All three must be provided. Okay, I will draw that up before I stop the video so you can go back and see what all three are, but we are definitely done. I apologize for running late. Go ahead and pack up.
When you say all three different ways to write that?
Yep. So I'm frantically trying to get it drawn in here so you can see it.
Is that what we have to do on the test?
Yep.
Will there always be an octane? What if there's 7 electrons?
There will not be 7 electrons. If there's 7 electrons, you screwed something up. At this stage, at least.
Where are we meeting tomorrow?
Ironwood 225. So U-turn. So straight through these walls, Hulk it through this wall and through the next wall, you're in Ironwood 225.
Okay, all right.
At 9.
Not at 8.
At 9. 9 this week, 8 next week.
I have a question. So how does it make it 6 when that